Welcome online lecture series with wireless mobile communication. Today our topic is parameters of the multi-part channels. So started from the parameters of the multi-part channels. Parameter of meters of multi-part channel. Many multi-part channels parameters are derived from the power delay profile because the power delay profile gives the intensity of the signal received through the multipath channel. So it is as a function of the time delay. Many multipath channel parameters meters parameters are derived from the power delay profile, that is abbreviation of PDP, because PDP gives the intensity of intensity of a signal received signal received through a multi-part channel. As a function of time delay. The time delay is the difference in travel time between the multipath arrival. What is the time delay? Time delay is the term time delay described the difference between the multipath arrival. Describe the is the difference difference in travel time between multipath signal component arrival. So PDP of this multipath channel is mathematically expressed. In our course, derivation is not required. So I am going to directly write PDP of multipath channel is mathematically expressed as mod of r of t naught का whole square is equal to 1 upon tau max integral of 0 to tau max and expression is t1 summation of k is equal to 0 to the n minus 1 attenuation of a of express small a का square t naught p square and impulse shift t minus t tau k t minus tau k and integrate d of t. This expression is power delay profile function, and the power delay profiles are measured using the uh, certain following techniques, and these techniques are as follows. Power delay profile are measured using the following techniques. First technique is time dispersion parameter. Time dispersion parameter person parameters Second is coherence bandwidth. Coherence bandwidth. Third is Doppler spread and the coherence time. Doppler Doppler spread and coherence time. Coherence time. And this is nothing but it is the graphical representations. So the power delay profiles are generally represented as a plot of relative received power as a function of access delay with respect to the fixed time delay reference. So move towards the graphical representations in terms of power delay profile. So power delay profile are generally represented as the plot of relative relative received power as a function of access delay with with respect to fixed time delay reference. So so we are going to see the first of all the input signal with respect to time in a free space wireless communication. It having the two types of the fading, large scale fading and small scale fading. In this figure you can see the dark black line that is shown by the large scale fading. On this scale there is a signal which is going to up and down due to fluctuation, rapid fluctuation in a short duration time during a small distances. So this is nature of the your small scale fading. Now see this diagram which is shown in front of you. It is the scale graphical representation uh, of a plot of relative received power which is normalized at dV scale in this dV scale at the y-axis, and at the x-axis we are having the another profile, that is the axis delay in nanosecond, and this is the with respect to the fixed time delay. So the received signal level versus to the time delay as a function of your measurement, you can see in this diagram. So before we are seeing this diagram, there is a one more things. uh, there is the okay, we are going with this figure. uh, in this figure, before you can see this figure, first of all uh, we see the graph between the received signal versus to delay time. We draw the two axes, y-axis and x-axis. So in y-axis we are having the received signal level, or in x-axis there is a delay time as a function of measurement, as a function of measurement. Now signal are like this way, this is our signal, and we put the some threshold and divided into the three region. This is the first region, and this is the second region. So this peak is shown, all peaks are shown the multi-path component, and this peak is the peak of fading. The near to in this region, the region is region 1. It is the near from the near from the reflection. So this fading is occur due to reflection mechanism. when the wavelength of the transmitted signal is more as arrival at the receiving end, so reflection is taking place. Now the second reason of this graphical representation, it is the signal from intermediate middle of the transmitter and receiver. That received signal get arrived at from intermediate middle of transmission and receiver. This area is known as region number 2. Now this area is known as region number 3, and the signal which are received at the receiver end, the signal from distant reflections. So the power level is going as a signal propagation from transmitter to receiver, either in indoor or outdoor environment. So power delay profile is typically uh, predicted in this diagram. So it is like this way. We having the threshold, and this is like, so in order to compare the different multipath channel and to develop some general design guideline for the our wireless systems parameter, which grossly quantified the multipath channels are used. So the graph which we are using uh, which are using is this one. So it is the graph between access delay, which is measured in nanosecond, and normalized received power is calculated in dB scale. So this is the graph having the two thresholds level. One it's fixed at 20 dBm, and another one is fixed at the 10 dB, minus 10 dB. One is at this point, another one is this is the threshold level. Actually we don't need to fix a more than one threshold, but for the seen the effect of the parameters in our diagram. So we fix the threshold as the 10 dB scale also. So there are the two fixing point. So let us see what is the effect of this observations. Now you can see here uh, the second peak of this second threshold minus 10. You can see this is the second peak of the your received signals, and when it touches the your this threshold second minus 10 dB threshold, from this peak to the last peak of your signal, which are falling in a minus 10 dB. It is the last peak of, after that it goes down. So the positive peak of from this minus 10 dB, the second last peak, second starting from the second peak, and the last peak, and the last peak. The distance between duration between this second peak and the last peak of the second threshold is known as RMS delay spread. So the RMS delay spread is the time duration, is the time duration between the square root of the second control moment of the power delay profile, and it is normally given by sigma tau, and it is having the value of under root tau square prime minus tau square, where tau square prime is the summation of, is the ratio of summation of k attenuation k a of k का square and r of k का received signal का square, and to the k, k of square to the k. So it can also be written as summation of power r of k to the summation of r k का square and summation of variable at p of tau of k. And the maximum access delay is the last peak of your arrival of multiple components above the second threshold level. This is the maximum delay, and it is always less than to the 10 dB, and it having the values of around 84 nanosecond. So the mean access delay means maximum access delay minus minimum access delay. So this is the first moment where the power delay profile has been calculated. The second highest peak values is going down, so it is started from this region, and this is the point where maximum access delay is calculated, and it is about the 45.05 nanosecond. So you can see the mean access delay donated by tau bar this is the first moment of power delay profile delay profile and it having the value tau r is summation of at k variable a of k the whole square tau of k to the summation at k a का whole square where random variable a of k, that is also equal to the summation of k at the power profile tau of k, then product of tau of k to the total power, summation of k to the total received power. So in this scenario, the component which we are using, this is the our tower base station known as base station, and it radiate these signals, and there is a ms mobile station, and there is one another things is object that is object, yes, scatter. One thing is also there, that is in the form of trees. So if the signal is directly fell on a mobile station, that is called line of sight. If the signal is reflected by the trees and there is also some terrains and cliffs, and so this is the first multipath signal is arriving at this. So we can write here, I can write the multipath 1, and when it is strike at human made buildings, and it is scattered at the sharp edge and reaches at your destination. This is a building. There is one more thing is car. This is multi path 2. When the transmitted wave will strike on an object and it reflected back to the receiver end, it is the multiple component multipath 3. So from this diagram we are seeing multipath, and it's provide the attenuation factor, which is described by A, given by A, and delay which is denoted by tau. So we generalize this and see x of t signal is transmitted over a channel, and at the MSB, this is base station, y of t. Impulse response of wireless and if we are seeing in a multi-path scenario, one from here to here, second path from here to here, third path, and so on. So multi-path one A1 tau 1. This is multipath zero. This is the A naught and tau naught. This is multipath to A naught, A2, tau 2, and all the multipath components till the last multipath at the L minus 1. So component is L minus 1 comma tau L minus 1. Now see the graph. ये है आपका amplitude. This is one is the amplitude at your y-axis, and in x-axis time. From line of sight we are getting this type of signals. From delay T naught, and the second tau 1 we are getting, and at the last AL minus 1, this is A1 attenuation function though, and it is due to cars and buildings. This is tau L minus 1. Suppose at base station transmitted signal x of t is equal to the signal now x of t is given by a delta a delta of t and impulse shift. Then this delta is known as signal then then at at mobile station we getting the output y of t receiving signal in terms of channel response h of t, that is equal to a naught delta t minus tau naught. This is LOS component, line of sight component, plus A1 delta impulse shift t minus tau 2 plus and so on a L minus 1 delta impulse shift t minus tau L minus 1. That is the non line of sight component. And the whole this thing is are nothing but multiple component. Why I am going to tell you, because I want to clear if any doubt in your mind. So this is the multiple component. So we write the equation, output equation y of t summation of I takes the value 0 to L minus 1 a of I delta impulse shift t minus tau of I, that is the for impulse input, and this is the delay component. And this one is amplitude amplitude component if a multipath if a multipath. So so RMS delay spread is the square root of second central moment of the power delay profile. And that is given by sigma tau, and it takes the value tau square bar minus tau square, where tau square bar is sigma k a of k square r k square upon sigma of k, a square of k is equal to sigma of k power of r of k, the power square of k divided by sigma of k into p of r of k. And maximum access delay is given by x in dv, and it is defined as the time delay during which multi-path energy fails to x dv below the maximum, that is x is equal to tau of k minus tau of naught, where tau naught is equal to first arriving sigma, and tau of k is maximum delay at which the MPC is multiple component is within XDVM. So we are having some more topic regarding to your small scale trading, and which is shown in the next class. So thank you. Now some